Hello student, welcome to today's session. So we are into the fourth session of the topic of isomerism. Till now we have placed 4 sessions in which we have talked about the structural isomerism. We are left with one of the form of structural isomerism is the topic of tautomerism. So seeing the length and breadth of this particular topic, we shall be placing 2-3 videos on this particular topic of tautomerism. So the objective of today's session would be that in today's session we try to understand what do we mean by tautomerism and what are tautomers and how they are being formed and what is the driving force which take one tautomeric form to another one. And then in today's session, in first 3 questions we try to address in this today's session, and in the subsequent session on tautomerism we also would like to address the topic of stability of tautomeric forms, for which you shall be requiring the understanding of GOC. And we also talk about acid catalyzed tautomerism and base catalyzed tautomerism and applications and problem based on tautomerism. So seeing the length and breadth of this particular topic, we shall be placing 2-3 more videos on this particular topic. But in today's session, we try to first figure it out what structural feature there would be there in a given compound to show the tautomerism. So as I said, structural isomerism, chain, position, functional, metamerism, ring chain, we have already placed videos on this particular thing, and today we are going to take up the topic of tautomerism. Now let us start with the discussion. Now if in case if I go to market to buy a compound named as acetone, if I just will place one hydrogen here, now this particular molecule is called as propanone in the IUPAC naming, and in common name we say it as acetone. Now if I just would buy a bottle of acetone and with some superpower energy, I critically would see that in that bottle of acetone, if with some superpower energy I just would identify all the molecules of acetone, if all the molecules of acetone are they present in this form only? If I would say all the acetone molecules are in this form, then I shall be wrong in my observation. Some of the acetone molecule happen to get changed into this form, where one of the hydrogen which is there onto this reaches to this oxygen, and between the carbon generates a double bond. So this ene is being generated and OH is also there onto the double bond. So we happen to say it has to be enol, and this has to be said as ketone. Now what basically I am trying to say it here, to begin with, what do we mean by these two? These two basically are, we can say it as functional isomers. These are functional isomers, isn't it? Both of these are functional isomers because function group in both of these two structural isomers are different. Now the point here is these two functional isomers cannot be isolated in pure form from each other. They are always in a state of dynamic equilibrium with each other. They are in the state of dynamic equilibrium. What I'm trying to say to you people is that if you just would see in a bottle of acetone, if all the molecules are in this form, then I will say it is okay, it can be isolated, but I am saying it is not that way. Some molecules of keto would change into enol. That if I would write its IUPAC name, it is 1, 2, 3 prop 1 in 2ol. Some molecules of prop 1 in 2ol is also there in a bottle of acetone, or vice versa. If you have a bottle of prop 1 in 2ol, some molecules of acetone is also there in that. That's a different story, which would be the endeavor of mine to explain in upcoming session what shall be the percentages. Generally we say keto form is more stable than that of enol. In this particular case, almost more than 99% is acetone and less than 1% is enol form. That's a different story. But here, to begin with, we first in this particular session, I am going to address this point that what structural feature do we require for a molecule to show tautomerism? What structurally you do see in a molecule, at least that it would show some sort of tautomeric form. So let us see and dig deep into it. Now the first basic thing which you always have to keep it in mind is, if I would do it in my style, let's say I have some functional group of the type XY, and this function group is containing multiple bond, either double or triple bond is there between X and Y, and along with it this XY functional group is polar in nature, there is polarity in that. Now, if this functional group, if ever would get attached to a carbon of the type sp3, and that sp3 carbon is containing at least one hydrogen, and such carbon which is directly attached to function group is also commonly referred to as alpha carbon. And this alpha carbon is containing one hydrogen, so this hydrogen can also be referred to as alpha hydrogen as well. Alpha hydrogen. So what I'm saying is, I have a functional group which is having a multiple bond, along with it there is a polarity in it. And similarly here also I can say this has to be alpha carbon, and this hydrogen can be said as alpha hydrogen, and it is having a XY functional group which is having a polarity. Now if structurally you would find ever this type of feature is there in a compound, then there are chances that the hydrogen which I am marking it with green, this hydrogen could oscillate between carbon and Y atom. So what this Y, which is delta negative, would snatch this H towards itself, such that this bond goes here, this goes here. As a consequence, you would get a double bond between C and X, and Y would get that H. And similarly here also, if I would do it the same thing, that this Y would snatch this H, this bond goes here, this goes here. As a consequence, you would get a double bond generated between CX, and here you would get this thing. And vice versa, it can reverse back in the similar way. This bond goes here, this goes here, and similarly this can go here and this go here. So these two are said as tautomeric forms to each other. That's a different story. What shall be the percentage of these tautomeric forms in the equilibrium? That's as we dig deep into it, we will address it. So what structural feature do we want to see into any compound? We shall be saying I need to have a polar multiple a function group which is having a polarity along with some multiple bond, and along with it should attach to at least with a carbon containing one alpha hydrogen, and that carbon must be sp3. Then only this hydrogen would oscillate between C and Y. And you would also see in some books this is also written to as to be, which I started with, is a triad system. Triad system means that if I mark this as 1, this as 2, this as 3, so 1 carbon 1 and Y3, these 1 and 3 atoms are the positions or the polyvalent atoms where this hydrogen keep on oscillating. So that is why it is called as 1,3 triad system. Now this structural feature which I have just referred to, X and Y function group, this type of a structural feature would be evident in the following cases which I am placing in front of you. First is the form where you have a keto group, CO group, adjacent to a carbon. If I would just now mark it like this, that this carbon this is sp3 carbon, and the hydrogen attached to this can be said as alpha hydrogen. This is a alpha hydrogen. Now what we can say here is that there is a polarity in this function group. CO bond is containing a polarity, and now what I can do here is that if this bond comes here, this goes here, what structurally do you get here is a sort of this type of a moiety. Is it okay? And this type of a structure which we get here is, this we refer to as ketone, and this is your double bond, and onto the double bond there is a OH group, so this is enol. So we will say it is to be keto-enol tautomerism. Now let me repeat, because this is the one which is which will be dealt in very detail. What structural feature we have just isolated. So you have a polarity CO bond, adjacent to this there is a alpha carbon, and the hydrogen attached to the alpha carbon is called as alpha hydrogen. This hydrogen has the tendency to oscillate between carbon and oxygen, and as a consequence you would get a double bond and OH get attached here. In general, we used to say that out of ketone and enol, to begin with, the keto form is more stable. This is generally more stable, simply because of the fact that the bond energy of CO group, if I would say the CO group's bond energy is generally much greater than that of C double bond C. That is the structural, that is the main reason why keto form is generally more than enol form. Here I can endorse one viewpoint from the book of Jerry March. This is a very important book of organic chemistry, Jerry March, and I think you would find, depending upon the addition you have, page 60, 70 or 71, you would get this understanding that if you have this ketonol tautomerism, here it is very categorically mentioned here is that here if I just would mark these bonds, these three bonds, if you just would see CH, CC and C double bond O, and here you have these three bonds, if you would just see the bond energies of this would require 12 kilocalories more energy to break these bonds. So simply because of the fact CO bond energy is greater than that of C double bond C. So here it is being endorsed very categorically. In journal, we will say 12 kilocalories more stable. Keto form is 12 kilocalories more stable than that of enol. That means you would require more energy to break CO bond as compared to C double bond C. Now, this we would be addressing in much more detail in the upcoming session. Today in the session, we just would want to show you that what structural feature do you require in a compound to show tautomerism, and what are the different types of tautomerism we can get with. So first is the ketoenol, which is the important one. This first one is the important one. Second is, if you have this sort of a compound, in this compound, this is delta positive, this is delta negative, and this is called as nitroso. This is a nitrosyl cane, and here you again would have sp3 carbon, and you also have a alpha hydrogen. Now what we can say here is, in this case also, if this bond goes here, this goes here, next structural feature you would get here is C, here you would get a double bond, and here you would get OH. So this type of a functional group which you ever would have seen is called as oxymate, or here it can be said as nitroso oxymato tautomerism. Only thing which you always have to refer, as I said in the start of the session, that you just have to pick the structural feature. If this sort of a structural feature is available, sp3 carbon, along with the viewpoint of a function group having a multiple bond, then tautomerism do happen. Similarly, you can see here also that this is delta positive, this is delta negative, and this is your alpha hydrogen, and this can move here, and this bond goes here, this goes here. As a consequence, what next structure do you get here is C double bond C in OH, and this is referred to as this is called as nitro, and this is called as Se, or at times you will also see a common name Se nitro. So this is called as nitro Se tautomerism. Nitro Se tautomerism. So this is also very, very important. And if we move further, you may also see a structural a compound of this nature. Now in this case, you again would see delta positive, delta negative, and if I move this bond here, wow, it is very interesting that if you are able to see, again you have to concentrate. If you are getting this sort of a feature in a compound, you definitely would see a tautomeric form generated here. Only the point is you have to be vigilant about the fact that the carbon, hydrogen, the alpha hydrogen which you are referring it here is should be onto the sp3 carbon. Why is it so? We would be explaining in some time in today's session only. So here you would get again a compound of this nature. Here comes the double bond between carbon carbon, and this would get one H here. And if I just would write it once again in a simpler form, so here I can say this is NH2. So here you have a double bond. Double bond means ene, and here you have got amine. So this is referred to then as enamine. And here you have this particular compound is imine. So this is a type of tautomerism which we call it as imine enamine tautomerism. Similarly, if I move further, this is called as cyano or cyanide. And here again you would find delta positive, delta negative. This bond goes here, this goes here. And now what you shall be getting here is a double bond between carbon carbon and NH. So here I can say this again is double bond ene, and this part or this moiety, this function group is called as imine. So this can then be said as cyano ene imine tautomerism. So this is again very, very interesting. Moving ahead, Now in this case, if you could see, this is basically amide. This is amide. And in the case of amide, this hydrogen can do the same thing. Here it is not sp3 carbon. Here is the point which you have to be little vigilant about, which actually would be addressed from the topic of GOC. Now if I just would explain it here, that you may argue on this point that this carbon is sp3 and it is having a alpha hydrogen as well. But here the point is the acidity of NH bond, if I would say NH bond versus CH bond, this is more acidic. This can lose H positive easily, and that why it would, this particular hydrogen or this H positive would oscillate more vigorously as compared to the carbon hydrogen. So here what we may then write it like this is, there comes a double bond here. If you just would migrate the bonds, this bond goes here, this goes here, and you would get something of this type. So this is sorry, here I should have written carbon. So here comes the carbon. So this basically is a you may refer to this as imidole tautomerism. Imidole tautomerism. So what basically do you get here in this case is of this nature, this type of a tautomerism. So here the question you may ask with that, why we haven't done this one? Because in the compound, the more acidic hydrogen always would get to undergo tautomerism rather than the hydrogen which is a part of a weak acidic part. So that is the reason why we haven't. So you should know that there is a type of a tautomerism which we call it as amide imidole type of a tautomerism. Now moving ahead, similarly again you have to structurally see, would this particular, if there is a this type of a structural feature is there in the compound, would it be showing tautomerism? Yes, it may show. Now if you just would want to see it in the form which we have shown in the earlier cases, is this one. This is the case. Now this N double bond N, wherever it is, this is a azo group. So this is basically azo group. Now this azo group has the tendency that if I just would do it this way, what structural feature do I get here in this case? Here comes the double bond and here comes the NH, and this bond get attached here. Or if you want to show it in this case, this goes this, and ultimately you happen to get something of this nature, NH. So this basically is called as, this is called as azo, and this is called as hydrazone type of a structure. So this is azo hydrazone type of a tautomerism. Similarly, if I would see into this particular entity, this structural feature, this is called as azo hydroxyl group or hydroxyazo. So here if I just would move this way, so what structure do I get here is something of this nature. This type of a entity is created here. So this part is called as nitroso and this part is amine. So I can say nitrosoamine, nitrosoamine, and this is called as hydroxyazo nitrosoamine. So these are some typical cases which generally would not be asked much. But let me conclude what I just have told you. Structurally, what you have to see to in a compound to show it a tautomerism, you need to have a polarity in a function group which is attached to a carbon which is sp3, and this is called as alpha hydrogen or alpha carbon, and this alpha carbon must have a hydrogen which is onto the sp3 carbon. So if this structurally, if it is there, if I would mark it in all of these, if you could refer here, we just have concluded most of the things. So in all of these there is a polarity. If structurally, if you would find, so have I not made the things easier? Just if these structural features are there in the compound, then there is high chances that that particular compound may undergo. I am referring a word may undergo because there are other things also which is taken should be taken into consideration as we proceed further from the GOC point of view, you are able to see many things in this discussion. That is why I am saying the length and breadth of this topic is quite a good one. So these are the some of the journal moieties which you would find that these structural features would can be showing tautomerism. So this you always keep it in mind. Now let us dig deep into the topic of keto-enol first, because that is the most important one, which is the part of our syllabus, and these other tautomeric form which I have shown, they may be asked in the paper. And along with, I may also show there is a diode system also, where two atoms, if I would say 1 and 2, here you have a lone pair. If this hydrogen happens to move to this side, what next structure do I get here is this carbon would get a negative charge and this would get a positive charge. In simple, we used to write it like this, and we just would say a coordinate bond is being generated, or in other form, if you just don't want to show the coordinate bond, then this is negative, this is positive. So this is a diode system which can be possible in the HCN. So this hydrogen keep moving from this position to this position and keep oscillating. So this is a diode system. Other cases which we have done it for the triode system. Now coming on to the keto-enol tautomerism. In the keto-enol tautomerism, first my endeavor is to let you know that how many tautomers we may generate from a given aldehyde or a ketone. That is the first point, and then we later on would address that whatever tautomeric forms or whatever enols you have generated, that which among them are more stable and why. What is the stability order and what could be the order of percentage of those tautomeric forms. That is the another discussion which we shall be doing in the next video. Here the endeavor is to tell you the tautomeric. So first you have to identify the function group. The function group is there, and this is the alpha carbon, and there is one alpha carbon into it, and there is there are 3 alpha hydrogens. There is availability of 3 alpha hydrogens into it. So what basically you have to do is that how to generate a tautomeric forms is just you have to bring it here, here. Next structure you would get CH2 double bond and OH. This is the structure which we get. So similarly, if I would move further here, this is the case of acetone. In acetone you have 2 alpha hydrogens, 2 alpha carbons. Alpha carbons are the carbons which are directly attached to the function group. Here you have 2 alpha carbons, and these 2 alpha carbons are chemically identical, and the hydrogens present on these alpha carbons are 6 in number, 3 on each, and they are chemically identical. So if they are chemically identical, you shall be getting only one tautomeric form out of it. So how can I show it? If I just would do it like this, if one hydrogen, I just would show you this bond goes here and this goes here. As a consequence, what next structure do you get here is the enol is generated like this. Whether you do it from this side or this side, the tautomeric form would be same. If I would show it from this side, then also it is same. So both are same, nothing different in this. Both of these are. So one tautomeric form you would generate if you have, even if I have 6 alpha hydrogen, I am able to get only one tautomeric form, because all the 6 alpha hydrogens are almost chemically identical. Now coming on to the next case. This is the case of butanone 2. In the butanone 2, you are able to see there are 2 alpha carbons, alpha and alpha dash. Here I marked this as alpha dash because this particular carbon which I am marking it with green, this carbon is attached to methyl group. So this is, since it is getting attached with a methyl group, so it becomes chemically non-identical as compared to the alpha carbon. So you have one alpha carbon and there are 3 hydrogens onto that alpha carbon, that is 3 alpha hydrogens. Whereas alpha dash carbon are 1 and the hydrogens attached to it are 2. So chemically you have 5 alpha hydrogens. If I would say I have 5 alpha hydrogens, out of 5, 3 alpha hydrogens are of one type and 2 are alpha dash. So this is the viewpoint which I just have marked it. Now since I am getting with me 2 non-identical type of alpha carbons, so hydrogens, so I shall be getting 2 types of tautomeric forms. One is this, where I just would move this one If I would move this one, this goes here. So the next structure which I shall be getting is one enolic form I can generate from this side, this direction, and the second enolic form which I may get is from this direction, that is from the alpha dash. And from the alpha dash, what I shall be getting is CH3COH double bond CH3. So this I got it from the alpha dash, and this I have received it from the alpha. So this is from this direction and this is from this direction. Am I right? I think I made my point clear. So you shall be getting two tautomeric forms from this. And similarly, if I would go for this, here you have two alpha carbons and two alpha carbons in containing two alpha hydrogens which are chemically identical. So since all of these are chemically identical, so if I would move this way, so this hydrogen comes here, so you would get a enol from this particular moiety like this. Similarly, if I would move further, here again is a similar case of butanone 2 type. Here you have two chemically non-identical type of alpha carbons. This is alpha, this is alpha dash. Alpha carbon is one which is containing two alpha hydrogens. What are those two alpha hydrogen? One is this, another is this. Similarly, you have one alpha dash and one alpha hydrogen. So there is one alpha hydrogen. So chemically you have two distinct type of alpha hydrogens. So therefore you shall be getting two different types of enolic form. One from this side, which I marked it with green, is this one. I am going to get this one. Another one which I am going to receive it from this direction. So that is which one is the one which we get from this direction. So out of this, in the subsequent lecture we will be addressing it, so tautomeric forms you are going to get two. Which one is more stable, that is the part of discussion of the next video from the GOC point of view. Similarly, here the point is, first structurally you should know what are the tautomeric forms, how it can be generated, what structure feature you should look for, and how many tautomers you would get from a given structure. Now this is the case where you have to address the topic from the point of view of activated methylene. Now what basically do I mean by activated methylene? If you ever have seen, let's say if I take this example here, I am talking of activated methylene. Activated in one what sense? Activated methylene or methylene. So first you have to understand the common name. If you see CH2, if somewhere CH2 is to be named, this is called as methylene, and this methylene is attached to two CO groups onto the adjacent side. Two CO groups on the adjacent side. When onto CH2 group, two electron withdrawing groups are attached, we refer to that CH2 group as to be said as activated methylene, in the sense that the acidity of that CH2 group got increased significantly. Because if I just would deprotonate this H positive, here you would get a negative charge. Now this negative charge, if I refer to this as acid, this would become its conjugate base. And this conjugate base is highly resonance stabilized. It got highly resonance stabilized. The negative charge got delocalized onto the two CO groups. So that is why it is very stable. Very stable due to, or I may say, resonance stabilized. So these topic we will be addressing in the next class as well, resonance stabilized. So if you ever would see a case of activated methylene, here you always have to remember that if I just would mark these two hydrogens, now see here, if I just would do it like this, that this is the one hydrogen and this is the another hydrogen. So this is alpha and this is also alpha, but I shall be saying this as alpha dash. Now if I just would mark the acidity of CH, which one? If I would say this CH is of alpha and this is alpha dash, so the acidity of CH alpha dash is activated methylene carbon hydrogen bond is highly acidic. So this would undergo deprotonation very speedily as compared to the other one. Now make it a point, wherever you in a compound or in a substrate you are having more than one acidic hydrogen, and the reaction engages acidity feature in that particular problem, the one which is more acidic always would participate as compared to the one which are less acidic. So here the point is, if you are being asked that how many tautomeric forms you would get for this, so we shall be saying this is alpha alpha, these two alpha carbons are chemically identical, 6 alpha hydrogens are chemically identical, and this is alpha dash. So principally we would say that the hydrogen which is of the activated methylene would undergo tautomerism because it is more acidic. The one which I have shown it, this one, if I would mark it once more for you, this hydrogen I have just said that this would undergo, this alpha dash would undergo tautomerism more eagerly as compared to that of alpha. Although theoretically we may say that some amount or in very minute quantity this may also be generated, but it is ignorable. So theoretically we may say that it can be generated from alpha as well as from alpha dash. Depending upon how the question is being framed in the MCQ, we have to address it along that way, because this can be ignored in some questions, but the quantity here, if I have to say it in the quantity, this would be 99%, and out of the two enolic forms, this is more than 99%, this is less than 1%, if I would consider only the tautomeric forms of the particular compound. Now moving ahead, if I just have to now take up some problems of this particular thing. So here, these all are the cases of activated methylene. In the case of activated methylene, the tautomeric form which primarily would get formed is from the activated methylene. In this case also, the quantity of, and the other reason for that is that when you do the enolization of the activated methylene, intramolecular H bonding also would be seen in the enolic form. So that particular discussion we will take up in the upcoming session, where some aspect of GOC is required. Here the only thing which I wanted to tell you is how you have to make the different tautomers and what structural feature you should look for. Now here comes the question. In this question, what you are being supposed to tell is that there are two alpha hydrogens they have shown. Alpha hydrogens are being shown, alpha and alpha dash, which would undergo tautomerism, and why. So here is a very important and interesting viewpoint. Here, of course, we are able to see this is sp2 and this is sp3, although this is alpha dash and this is alpha. So alpha carbons are containing 1 hydrogen, but this part of the molecule would not undergo any sort of tautomerism. If in case I do, if in case I do show you the tautomeric form formed from this direction, it would not give you a right answer. The first viewpoint is, this is the thing which is being given to you. Let me mark it once again for you. So this is the hydrogen. Now if I just would say this, although this is a alpha carbon, but the carbon is of the type sp2 whose bond energy is greater. So first you always have to remember sp2 s bond has greater energy than sp3 s bond of carbon hydrogen bond. Now the point here is, if in case I just would do the tautomerism, just see here. Now if I do so, what next structure do I get here? Here I would get OH, here you would get a double bond, here also there is a double bond. Now what you have made in a cyclic structure, this carbon has become sp hybridized, which always would want to become linear, and this bond get broken just to acquire the linearity. So this would not undergo tautomerism. Whereas the one which is on the sp3 side, this definitely would easily undergo tautomerism, and it would bring in resonance also, which would provide extra stability. Now this goes here, and this bond goes here. So as a consequence, what next structure do you get here is something of this nature. Here comes the double bond, here comes the double bond, and OH, and this is definitely going to take place. So alpha dash hydrogen tautomerizes, and in doing so it tautomerizes, and in doing so it also bring in the stability in terms of resonance. So this alternate pi bonds can undergo resonance in both directions. So this in a way provides a extra stability. So that is why you need not to go in this way that as in when you see alpha carbon containing alpha hydrogen, it would tautomerize. Generally people do this mistake. That carbon which is alpha and is containing one hydrogen should contain a hydrogen which is of the type of sp3. Okay, so let us move further. There are lot many things into it, just like in this question. Again, very beautiful question. Here they are asking alpha, beta, gamma hydrogens are being given. Which out of this would undergo tautomerism? So here we said this is a sp2 carbon, this is sp2, this is sp3. Although this is sp3, but this is not alpha, this is a gamma carbon. So the point is, till now I am keep on saying that you need to have a alpha carbon, along with it should be sp3 and it should have alpha hydrogen. But at times you would find that it is not always that way, because here I require a help of GOC. Now see here, if I do so from the viewpoint, if I do so like this, the next feature which I would get here is a entity of this type, isn't it? I would get a tautomeric form of this type, but this would not happen because this carbon has become sp and it always would want to become a linear, and it would create a lot of strain, and two pi bonds adjacent to each other in a cyclic form is highly unstable. So this would do a pi repulsion also. So this would not be possible. So this would not happen. Whereas if I would take the gamma carbon in this case, it beautifully will do the tautomerism. Just see it, because it will bring in a viewpoint of aromaticity. It would create a aromatic character here, double bond here, and here you would get a enol. Wow. This is interesting. Now the point here is that we should not stuck to this point that it is only the alpha carbon or alpha hydrogen. At times it is gamma carbon also containing a gamma hydrogen of the type sp3. This also undergo tautomerism, because why is it? It is almost forward driven. 99.9% would be the phenol or enol form. So why is it forward driven? Is because of the fact that it has brought a lot of aromatic character into the structure, and which provide a extra stability to the molecule. Similarly, let's take up few more interesting question. Would this undergo tautomerism? Yes, definitely. Here you would see this is containing carbon hydrogen, isn't it? This is alpha carbon and it is sp3 and it is having hydrogen. So you have 6 such hydrogens which are chemically identical. All of them can undergo tautomerism in the way that if I would bring it here and this moves here, similarly if I would bring it here and move this here, and similarly if I would bring it here and move it here, so what basically you would get here is, again you would get a aromatic character. So here you would get OH, OH, OH. So here double bond, double bond, double bond. So since it brought in aromatic character, so all of these hydrogens which are there on 3 alpha carbons would undergo tautomerism. On the similar viewpoint, let us take up one more very interesting question, that draw the tautomeric forms of following compound. This particular compound is being given. So here first you have to mark this viewpoint. Structurally what you have to see, that do we have this feature in this particular compound? Yes, I do have, because if I just would place NO here, delta positive, delta negative, so along adjacent to NO you need to see a carbon. Now adjacent to this you have a carbon here, here also you have a carbon, here also you have a carbon. Now that is this carbon which I am referring to. Now we have to see, do it have any hydrogen? Yes, it is having one hydrogen here. This also is having one hydrogen. This also is having one hydrogen. Now we have to see, would it be undergoing sort of tautomerism? Let us see, let us do it on to the next page. So this is the feature, delta positive, delta negative, and this is the carbon hydrogen bond which I was looking for. So here you have a hydrogen, here you have a hydrogen, here you have a hydrogen. Now how could I do the tautomerism? So I can simply do it like this. This bond goes here, this goes here, and this H get attached here. Similarly this goes here, this goes here, and this hydrogen get attached here. Similarly this goes here, this goes here, and this H get attached here. So in doing so, what structurally do I get here? I shall be getting double bond NOH, here also NOH. Now this would turn up to a very interesting problem. Now we got this thing. Now you just would see that in this structure which we have generated, again I am able to see the same X double bond Y type of a structure, and which is having a polarity delta positive, delta negative. Now what I'm trying to say here is this thing. As I do, you are able to understand it, what I'm referring here. Now if I just would place out of, there are two hydrogens, I am just placing one hydrogen, I am showing one hydrogen only, whereby I will do the some sort of tautomerism. Just see here, if I will bring it here, this moves here, in the process this hydrogen reaches to that nitrogen. Similarly, if I would do here, this goes here and this hydrogen reaches here, because this nitrogen would get a negative charge, then it would reach here. Similarly, if I would do this, this would go to this negative charge, go to the nitrogen, and this hydrogen comes here. So in doing so, what structure, now you would get something of this nature. Here you would get a double bond, here also double bond, here double bond, here comes the single bond, and this receive one H, here also it receive one H. Wow, beautiful, interesting, I'm loving it. So it's a wow problem. So this means the tautomeric form which we have made is this particular form may tautomerize to this entity, which this is nitroso, and this happens to get changed into oxymeto, and this further get tautomerized to hydroxylamine type of a thing. This is hydroxylamine, or you may also say it as to be. So this is what we have received. So this is a very, very interesting and beautiful question which I wanted to share it with you. Now let me conclude. What we have done in today's session is that we structurally find it out. We structurally found that what structural feature do we have in a given compound to show the tautomerism. So you need to have a function group which is having a polarity attached to a carbon, which shall be sp3, and it must be having one hydrogen, which we are referred to as alpha hydrogen. In the subsequent lecture, we also would now try to address the stability of tautomeric forms in the next class, and we also will bring in that tautomerism get catalyzed by acid catalyzed tautomerism and base catalyzed tautomerism. We also would speak on to the topic of kinetic controlled tautomerism and thermodynamically controlled tautomerism. And lastly, we will do some problem solving on to the, because this is a very lengthy topic which get repeated in the chapter of aldehydes and ketones. Thanks a lot. Have a nice day. Hope you have liked today's session. In case you liked it, do subscribe to my channel and share it with your friends and juniors so that we can make a community of chemistry loving people. Have a nice day. Stay safe and take good care of yourselves.